Okay, looking back on our gravitational potential energy just as a review, and then we're going to go into what's called escape velocity for our planet. We said that force gravity is g m1 m2 over r squared, okay, for any two objects, and this equation is most useful when we are farther away from the Earth. A reminder that work equals force times distance. So when we look at this equation, a force times distance is very difficult to do because our distance is constantly changing here. Okay, and gravity acceleration is constantly changing. So what we did is we took the integral from r1 to r2 of our force gravity equation. So integral r1 to r2 g mm divided by r squared dr. And then we're left with this equation here. We pull out the constants in front, and we integrated 1 over r squared dr from r1 to r2. We get this equation here, negative g m over r over the definite integral from r1 to r2. Plugging in r2 and r1 and subtracting them, we get this equation here, negative g m little m times 1 over r2 minus 1 over r1. Remembering that capital M stands for the mass of the planet, and little m is the mass of your object. Okay, how do we deal with this then? Essentially, I factored the negative in there, and or distributed the negative in there. We got delta GPE equals G big M little m times 1 over r1 minus 1 over r2. Now that gives us units of joules for gravitational potential energy. Because essentially, if we take force gravity and multiply that times r, we will then take one of the r's away, right? And we're going to be left with g m1 m2 over r. And this is a force, and that's a distance. So you'll be left with Newton meter as units. So that's joules. So that's kind of the cheating way to say, hey, our equation is a valid equation. Now what about escape velocity? Well, imagine blasting off with such a great velocity that all of your kinetic energy converts to gravitational potential energy. And at the instant you disappear from the Earth or break free of its gravity, all that kinetic energy went into the change in gravitational potential energy. We're now going to say that your second radius is when you're infinitely far away from the Earth and therefore have no gravitational attraction associated with the Earth. So then, again, kinetic energy goes to change in gravitational potential energy. So I'm going to say 1/2 mv squared is equal to big G, capital M, little m, times 1 over r1 minus 1 over r2. Okay, now what happens to this side here if I'm going to infinity on the bottom? Well, of course, that becomes 0, because 1 over infinity is going to be 0. So essentially what I have here is I'm going to just kind of make that as 0 there. I'll just write 0 on top of that. And then I have 1/2 mv squared equals g big M little m times 1 over r1. Now what's r1? Well, r1 is the radius of your planet, right? Because that's where you're starting from. You're starting from the surface of that planet. And then we recognize that m's can cross off on both sides, and we can solve for velocity. Dividing 1/2 to the other side and taking the square root, escape velocity then is going to equal this equation. The square root of 2g big M divided by r. It's very similar to the orbital velocity equation. So this time, of course, m does stand for the mass of the planet, but r stands for the radius of the planet, the original location here, and that will always be specific to whatever planet you have. Therefore, the mass of the planet and the radius of the planet determines the escape velocity, okay, from that planet's orbit. So when you solve for that, that would be how fast you need to go to break free of the gravitational attraction of that planet.